Hi everyone. So in our last video we began to look at differentiation of a vector field, and we found that if you take the derivative of a vector field t with respect to one of the coordinates xi, in general the answer for that is another vector field, and it can be written like this. So these are the contravariant components of this new vector field. Okay, so here are the basis vectors, and here are the contravariant components, which we denote nabla I tk. Okay, so we call it the covariant derivative of tk with respect to nabla I, and we saw that it was given by this formula. Okay, so the covariant derivative of tk with respect to xi is given by first term, just the usual partial derivative, so partial of tk with respect to xi, and then plus this extra term which has in it these Christoffel symbols. Okay, these all-important Christoffel symbols, which we have a general formula for like this. Okay, although I mentioned that in practice, when we want to find the Christoffel symbols for a particular coordinate system, we would almost never really actually do it this way. So as we shall see shortly, there are other easier ways, but this is the general formula. And so what I want to do in this video is just to talk a little bit more about these covariant derivatives and these Christoffel symbols and some of their properties. Okay, so going back to this equation where we have the derivative of a vector field with respect to xi, and I said that's another vector, and these are its contravariant components, okay, so multiplied by basis vector ek. You can just as well write this new vector field in its covariant form. So what I mean is, I can also write dt by dxi is equal to some covariant components times the reciprocal basis vectors. Okay, so E superscript k, and these components are denoted as follows. So nabla I t subscript k, and I'm not going to go through all the working here, although I show it in the PDF notes online, so you can have a look there. But it turns out that this covariant derivative, okay, so the covariant derivative of covariant components is given as follows. So this is where nabla I t subscript k is equal to, and the first term is once again just the usual partial derivative, so dtk dxi, and then it turns out, and you can see it in the notes online how it happens, it turns out that you get another extra term like this, but it's got a minus sign instead of a plus, and then you have a Christoffel symbol with a t, and this will be j, j, I, k. Alright, and the Christoffel symbols again, now the indices are in different places, but it's still given by this formula here. Okay, so you see these two formulas here. Okay, so the formula for taking the covariant derivative of a contravariant vector and the formula for taking a covariant derivative of a covariant vector. So this and this you should know off by heart. Okay, absolutely, you should know that by heart. And in fact, you can then generalize even further, and I won't show again the details of where it all comes from, but you can take covariant derivatives of tensors. Okay, so more general tensors, not just vectors, but higher ranked tensors. And to illustrate how that is done, let me just do it by way of example. So let's just look here at rank 2 tensors for handiness. So let's say we want to take the covariant derivative with respect to xk of tij. Okay, so imagine we have a rank 2 contravariant tensor tij, and we want to take the covariant derivative with respect to xk. How do we do that? Well, the first term, again, is just the usual partial derivative. So it's just dtij by dxk. And here's how you do the rest of it. Okay, so for each contravariant index on your tensor. Okay, so here there are two of them. For each contravariant index, you get an extra term like this, okay, with a Christoffel symbol and a T and a plus sign. And then for each covariant index on your tensor, now here we don't have any, but in general for each covariant index you get a term like that with a Christoffel symbol, a T and a minus sign. So in this case what we have is the usual partial derivative and then plus, and then the next term, and I'm just trying to almost verbalize my thinking for how to memorize the formula. So you've got a Christoffel symbol, so just draw a gamma, and then you have a T. And okay, look at your two indices. Okay, so let's have this term being for the first index, the I. Okay, so what you do is on the T here, you change that I index into a brand new dummy index. Okay, so up here the dummy index was called J, but let me call it something else here because I already have J as a free index. So let me call it A. So A, J. And then that upstairs dummy index has to get matched with the downstairs dummy index on the Christoffel symbol. And then you must also have I upstairs and K downstairs. So the I goes there and the K goes there. Okay, and then now we do the same thing for the J index. So plus Christoffel symbol, T. So we keep the I there, and now we replace J by a dummy, so A. And then a dummy goes down here on the Christoffel symbol as well. So that's summed over. And then we must also have J upstairs and K downstairs. So they go there and there. As for then taking the covariant derivative of a rank 2 covariant tensor, again the first term will just be the usual partial derivative, so dtij by dxk. And then you're going to have terms like this with a minus sign, so minus Christoffel symbol and a T. Okay, so the first term, let's replace the I with a dummy A. So we'll have AJ, and the A downstairs has to be matched by an A upstairs, so it can go there on the Christoffel symbol, and then we must have K and J downstairs. No, sorry, K and I downstairs. Okay, we've already got the J here, so it's just K and I. And by the way, it's worth pointing out, even at this point, the Christoffel symbol, so we will write this down properly later, but the Christoffel symbol is symmetric in the lower two indices. Okay, we'll see that later, but you can write Ki or you can write Ik, doesn't matter. And anyway then, the other term is another minus sign, Christoffel symbol, T, and then we keep the I and we replace J by a dummy A, so A here, A upstairs, and then we must have K and J down below. And what about then if we had a mixed tensor? So covariant derivative of K, T, I upstairs, J downstairs. Well again, the first term is just the usual partial derivative, so that's just dt I j by dxk. And then for the upstairs contravariant index, we have a term with a plus sign, so plus T, and then we put an A here, J here, A goes downstairs, and then we must have I upstairs and K downstairs, like so. And then for the downstairs index J, we get minus Christoffel symbol T. And then we have the I upstairs and the A down here, and then that's matched by an A upstairs on the Christoffel symbol. And then we must have J and K there. And maybe also I should just point out, I'll just write this one at the side. If you have a covariant derivative of just a scalar, so a rank 0 tensor, that is just, you only have this term, okay, so you don't have any terms with Christoffel symbols, so it's just the partial derivative. Okay, so the next thing we're going to look at now, now that we have the recipes for how to get covariant derivatives and we have a formula for the Christoffel symbols, we're just going to look at some further properties of covariant derivatives and Christoffel symbols. Okay, so the first couple of properties then of covariant derivatives that I want to mention are the sum rule and the product rule. So just like with ordinary differentiation, if you differentiate where you differentiate two functions added together, that's just the sum of the two derivatives. The same thing is true with covariant derivatives. So you have a sum rule. So if I take, for example, a covariant derivative of, let's call it Aij plus Bij, that is just the covariant derivative of the first tensor, Aij, plus the covariant derivative of the second tensor. Okay, it doesn't matter what the rank of the tensor is, or if the indices are all upstairs or downstairs. It's true in general. You also have the product rule, which says that if you take a covariant derivative of two tensors multiplied together, so say you have Aij b L, this is just the covariant derivative of the first, so covariant derivative with respect to xk of Aij times BL, plus then the other way around, so Aij times the covariant derivative of the BL. Okay, and then going on to the Christoffel symbols, we have some properties of those. So, as I already said, the Christoffel symbol, gamma Kij, is symmetric in the lower two indices. So gamma Kij is the same as gamma Kji. There's a short proof of that in your PDF notes. And it's also really important to point out that the Christoffel symbols are not tensors. Okay? Okay, so in general, just because I take some letter, in this case a capital gamma, and I put some indices on it, some upstairs, some downstairs, that doesn't make it a tensor. Okay, so to qualify as a tensor, it has to satisfy the required transformation law for a tensor. Christoffel symbols don't. Okay, so that's why they're called Christoffel symbols. Okay, if it was a tensor, it would just be called the Christoffel tensor. And again, a proof of that in your PDF notes. Okay, so if you look in there, I derive the actual transformation rule for the Christoffel symbols, and you can see that it's not the same as the transformation law for a tensor. However, covariant derivatives are tensors. So covariant derivatives are tensors. So for example, if I had gamma k ti, sorry, nabla k ti, so covariant derivative of ti with respect to xk, that is a rank 2 tensor with an I upstairs and a k downstairs. So a mixed rank 2 tensor. Okay, and the final thing I want to write down in this video is another way of finding the Christoffel symbols. Okay, so earlier on I gave you this formula, so gamma Kij is equal to the derivative of basis vector Ej with respect to xi dotted with reciprocal basis vector Ek. And I said that although this formula is true in general, we will hardly ever use it to find Christoffel symbols, because in general these basis vectors are nasty, okay, especially this one can be hard to find. So just this can lead to a lot of messy algebra. Turns out there's a simpler way, okay? In fact, there are a couple of simpler ways, but we'll just write the first one here. for now. And there's another formula that lets you get the Christoffel symbols, so I'll write it here, directly from the metric tensor. Okay, so you can forget about finding the basis vectors and taking these dot products. If you have the components of the metric tensor, you can get the Christoffel symbols as follows. So gamma Kij is a half times, and then you have the metric tensor in its contravariant form, so GKA, so this is this K, and then A is a dummy index, and then times some derivatives of the metric tensor, so you have dg dx plus dg dx minus dg dx, and then here you will have ija I. Okay, so again, this formula is proved in your lecture notes. Would you be expected to memorize that and know where all the indices are? No, I wouldn't expect you to. Okay, so if I wanted you to use this formula, under exam conditions or something, you would always be given it, or perhaps asked to derive it from somewhere. But as you can see, no basis vectors or anything complicated like that, just the components of the metric tensor and some derivatives. Okay, and this here, these three terms are the covariant metric tensor, so the indices are downstairs, and here, this one on the outside is the contravariant metric tensor, so indices upstairs. So those are some properties of covariant derivatives, Christoffel symbols, and I appreciate up to now this is all very formal, all very theoretical. What's the point of it? Where are we going with this? Well, what I'm going to do in the next video now is just use the theory that we have so far, and I'm going to take an example of a coordinate system, and I'm going to find the Christoffel symbols using this formula. Okay, so that would be quite a typical thing you could be asked in a test or on an exam. You could be given a coordinate system and asked to find the Christoffel symbols. So in the next video, we will have an example of that.